So you can just go ahead and unmute yourself. So there's a question in the chat. Will there be another opportunity to ask questions prior to the second exam? Yes, probably yes. Maybe not to the same extent. Maybe. Yeah, I think we can also take one or two more Q&A sessions prior to the second exam. Yeah, right, like a general Q&A session. Maybe.
Can we create our own A4 paper sheet for the exam, like a little for some notes, or is that prohibited?
No, this is not part of these exams. So I mean, practically, no aids are allowed at all. So no cheat sheet, no calculator.
So
Basically,
to remember some of the formulations by head then.
yes, exactly.
Okay.
All right. So there's one question in the chat. Can we solve exercise sheet 11, exercise 1? Let me see. Sheet 11. What's that again? That was about boosting, right? So I think it's okay. I mean, I think this one is better to be asked than in the Q&A session that was about boosting. So I can just give you the general idea. So I'll show you the former solution, that one. Give you an idea. Share my screen. Right. The one was about boosting. And the task was to basically first draw a boosted classifier, right, which consists of a bunch of linear classifiers and define the weights of this classifier. So there can be more than one solution, right? But basically, yeah, changing this classifier. But I guess the main idea is you have three linear segments, right? And each segment can be described by two or three data points, right? So for example, this segment that separates x2 and x3 can basically give one half weight to the data point x2, one half to the data point x3, right? And then you get this specifier. So yeah, I wouldn't go too much into detail because the focus of this exercise session are other topics. What is the structure of the exam? How many tasks, points in total? How much points for programming part? Okay, so for the structure of the exam, I can recommend you to look a bit at the older exams, so you can find some on Freitagsrunde. Show you the link. So these are, oh, where is it? Looks like they changed something. No, here it is. I'll send you the link, but these are not, I mean, these are like Gedankenprotokolle. These are not official exams. Mm. But I mean, at least the structure is basically the same. So 1/5 of the total points will be programming. Yeah, five exercises in total. 1/5 is multiple choice. Basically 5 exercises. One is multiple choice, one is programming, and then there are 3 theory questions. Yeah, 100 points in total. Will there be any formulas given, like in the exercises sometimes? Yes, yes. Yeah, so usually you're given some formulas, right, that you already know, and then supposed to apply the whatever, like maximum likelihood for something to it. Yeah. Will there be tasks to XAI? Yes. I mean, I'm not saying this definitely. I'm just saying XAI is part of the lecture and can also appear in the exam. Is it possible to attend the second exam on March 25th if I fail on the first exam? Yes. So we hope that we can grade Friday's exam rather quickly. Also, we have results sometime next week. Then there will be a rebuttal for the exam. You can review the exam, right? And then after that, you can decide. I mean, basically, if you fail, then you can write the second exam. It's a bit schedule is a bit tight this semester, but I think it will work. Is it possible to make deregistration for the first exam? I saw that until today night and register the second exam. Yes. I think you should be able to unregister. Let me quickly check. Mm, it's actually not so easy to find out. All right. So, okay, I think it's possible until Wednesday night. You can unregister until Wednesday um, midnight. How to best prepare for the programming part. Right. So basically the same way as for the theory part. So basically go through the homework, try to solve it again, try to do it without referring to the documentation, just so you know some of the basic functions that you need. Like, should know how some of the NumPy functions are called to, for example, uh, compute an inverse or pick a random index or these basic things. So if you would need something that's a bit more uncommon, then there will be a documentation, but you should know some basic NumPy in Python. Another question: will the programming part be strongly oriented on the exercise programming class? So nothing that we haven't seen somewhere. I mean, it won't be exactly the same, right? But also not something that was not exercised. So let me quickly check what we did in the homework. Yes. So, yeah, it will be close to the homework. Yeah. Yes. Yeah, right. So basically not exactly the same, but maybe it's like a different kernel or different loss function or something like this. No? Adrian asks, will the 3 out of 5 questions be divided by topic? For example, one topic area will always be question 1, etc. Or will there be sub-questions always be the same topic? I'm not sure I understand. So, I mean, there will, yeah. If there's like a question about boosting, then there will be like 3 to, I don't know, 3, 4, 5, 6 sub questions that are about boosting. But I mean, different aspects. Is there any question that we have to explain or interpret something in sentences? Yes, it can be. Might happen. Yeah, I mean, you can look at the older exams on the site that I sent earlier. So sometimes you will be asked to describe what an optimization problem does on a kind of a high level, right? Or draw something. There's this follow-up question. So in these 3 out of 5 tasks, there will be only 3 lecture topics included. Yeah, basically, yes. Yeah, right. Overarching. No, not really. Not really. I mean, there are concepts that appeared many times, right? Like Lagrange uh, optimization, for example. So, but this is not overarching. Mm. Okay, there's a question. What about boosting? I don't understand this question. Mm. I think boosting will have its own Q&A session. Let me quickly check analysis. All right, I see. Boosting. Uh, boosting will be later today, from 4 to 6. There will be a Q&A session by Hannah Ringwald. Yeah, so I think it's better to ask question about boosting there. How is the grading scale determined? I've heard that it's always slightly different. Yeah, right. So, yeah, I mean, the difficulty of the exam is also slightly different every time, right? So how we do it is basically um, fit fit the distribution of points to a normal distribution, mm, and then like the top 10% are the best grade, full points or 1.0, and bottom 10% will fail. I mean, typically there's a bottom of around 10% of people who obviously fail. So if you, I mean, yeah, basically, um, I think before the fairway, so that the grades are comparable between semesters, although the structure of the course and the type of and the exam is different each time. Can you explain Shapley values? Value that shows how much an input feature contributes to the output. Yes, I can. So there was an exercise about it. Um, I quickly look it up. AI. Um, no, with AI. Here we go. Let me share my screen. There was the slide about Shapley values, right? And the way it works is essentially for every of your input variables, you check how does the output of your function changes if you include or exclude this one variable. So there's a special case of Shapley values where you have all your variables, and you remove each variable individually, and you record how much does the output change. This is called Banzhaf values. Was not covered in the lecture. No? It's just like a simple special case. And Shapley values are a bit more complex because you build a set of all possible collisions that contain or not contain your input variable I, right? So these are called collisions, and these are just all the subsets of variables. So there's really a combinatoric explosion here. There's this weighting term that involves some factorials. So there's a reweighting so that basically small collisions have the same weight as larger collisions. And you always compute the difference between including your variable I to the collision or excluding it. And this way you get like an average of under all possible subsets of variables. How much does the output function change by including or excluding one of the variables? And this is then your contribution on this phi I. So what you need to compute is this weighting term that only depends on the size of the collisions, right? And evaluate the function with the variable I and without the variable I. So we did this, the way we presented it in the lecture is as this kind of table, where you have one column for the collisions, then one column for these weighting terms, these weights that only depend on the size of the collision and the total number of variables. And then this delta, which is how much does the output change by including or excluding variable I, right? And where you essentially you get all these terms. So you get the weights, you get the deltas, and you sum them up, right? I mean, you multiply them together and then sum them up. And then, there's like one trick that simplifies it a little bit, that by conservation, you can always, if you know n-1 or d-1 contributions, you automatically get the last one for free due to this conservation, and this conservation property is just saying that the sum of your contributions is equal to the output of your function, which means if you know d-1, then the last one is just the difference between the sum of the d-1 contributions and f of x. So this is one little trick we also saw. Conservation property. Yeah, so this is just a quick recap of Shapley values. If you have more specific questions, then go ahead and ask them. How will the programming part be graded? Do we get partial points or setting it up semi-correctly, or does the program have to work? All right, so I mean, it does not have to, it doesn't have to compile. I mean, there are things in Python that are not easily expressed on paper, like indentation of loops and so on. So yeah, I mean, there are things that are not really graded. So it's always possible to get partial points, right? So even if you don't know the syntax of a function exactly, if you write it as some kind of pseudocode, then you will still get partial points. I mean, it has to be stepwise. Like, you cannot just write a pseudocode that does exactly what you want, and it's just one line of code. It doesn't give you points, but really have to make it step by step and show that for each step, you know that it's something that can be done in NumPy easily. Right?
I have a follow-up question to the Sharpie values.
Yeah.
So there's like these brackets, the empty brackets, right? That's
Yes.
the set, I guess. And how do you decide on the set? So if it's an empty set or like if you have a true, where does that come from?
All right. So this is, do you see my cursor? Yes. My mouse cursor?
Yes.
Yes. Okay. So here you see it's a sum over all the sets S that don't include the variable I. Right. So we compute phi1. We build all the sets that do not include the variable 1, x1. Which is the empty set. It doesn't contain the variable 1, right? The set consists of only variable 2, only variable 3, and 28. Okay. So all possible subsets that don't contain variable I.
Okay, thank you. So 2 and 3 are like the variable number.
Yeah, exactly.
Okay.
Exactly. It's like the index of the feature.
Thank you.
Yeah. Okay, another question. Will the programming part be based on the 3 out of 5 theory parts, or is it not related? Usually it's not related. Might be, but typically it's not. Yeah, basically just to have a lot of variance between the exercises. In the past exams were some questions about discriminant functions. Could you explain what functions qualify as discriminant functions? Right. So this relates to the very first lecture about base decision theory. Let me quickly look up the slides. All right. Hmm. Here you go. There was this slide. Do you remember? So we started with these posterior distributions, right? It looks like this on the right-hand side. And according to Bayes' decision theory, you're supposed to always predict the larger class, the class with higher posterior probability. And we saw that it's below. Here we can use Bayes' theorem, and then we can still manipulate this function, this right-hand side, without changing the argmax. So everything that doesn't change the argmax is allowed. So typically, things that don't depend on J can be multiplied out or divided out, like here this P of X. If you do it for each of these terms, for every J, the argmax doesn't change. And there's another one that is quite useful, is this invariance under strictly monotonic functions. So whenever you apply a strictly monotonic function to each of your functions, it also doesn't change the argmax. So it really preserves the decision boundary. Yeah, right. So basically, monotonic functions like taking the log, or if your argument is non-negative, like here, you could also square it or things like that. So if you apply strictly monotonic functions, then you always preserve the decision boundary, and then yeah, basically this is how you build discriminant functions. So all of these functions, all of these guys on the right-hand side, they are all discriminant functions. I hope it answers the question. I mean, any function can be a discriminant function, but the way we use it is, yeah, as I outlined. Do we need to learn other libraries than NumPy, such as SciPy or scikit-learn? Okay, so let's say if something is requested that is not SciPy or scikit-learn, that is not NumPy, then you will get a bit of documentation, the documentation page for the respective function. But typically NumPy is all you need for the Excel. Or let's say maybe sometimes there's something that is a bit more abstract, like we say you have a quadratic solver, it has this syntax, and then yeah, you just use this imaginary function. Would you like to explain why the integration over the likelihood in a Bayes posterior estimator results in a normalization term? Usually is the evidence. The integration over the likelihood in a posterior estimator results in a normalization term. Okay, so it was it's a question about parameter estimation. It was lecture 2. Let me pull up the slides. here, right? So the posterior and there's this integral, right? Yeah, and you know from probability theory that a density like this P of theta given D, this blue function, it's a probability because it's non-negative and it integrates to 1. So if you take and you see the numerator and the denominator, they're basically the same, no? Except that the denominator is integrated over theta, right? So now if you integrate the whole thing over theta, then the denominator, it's actually independent of theta because theta is integrated out. So this is a constant. Now, if you integrate the numerator over theta, then you get exactly the same thing. So you see that the whole thing integrates to 1. So you divide by the integral to ensure that the integral over the whole thing is equal to 1. Yeah. So in this way, it's a normalization term. Okay, then there's a bit of a discussion. I have a question of it's lecture 1, base decision theory, the spam classifier example. PPT 1625, when features follow Bernoulli distribution, why the formula and the probability uses plus rather than times in the middle. Okay, so this I have to check. Could be that there's a mistake. The slides. It's possible. Slide 16. Indeed. Yes, you're right. Yeah, it's indeed, it should be multiplication. Yes, I can confirm. There's an error on the slides. Yes, and also on slide 17. Yeah. I'm just looking at the Baiduda and hard about discriminant functions. Okay, so I think there's a good paragraph in the book by Duda and Thought about discriminants, right? So they say there are many ways to represent classifiers. One of the most useful one is in terms of discriminant functions, gi of x, and I is the index of our classes. And we decide for class I if gi of x is larger than gj of x for every j that is not I, right? So this is this argmax argument, right? We use a discriminant function to make a decision based on the argmax. And here below he says, clearly the choice of discriminant function is not unique. We can always multiply all discriminant functions by the same positive constant or shift them by the same additive constant without influencing the decision. More generally, if we replace every gi by f of gi of x, where f is a monotonically increasing function, the resulting classification is unchanged. This observation can lead to significant analytical and computational simplifications. In particular, for minimum error rate classification, any of the following choices give extent identical classification results, but some can be much simpler to understand or to compute than others. And then you see exactly the steps that we took in the lecture, right? So multiply by a constant or apply the log. Yes. Okay, another question. Can you explain the Taylor expansion task again? In particular, I don't understand the last step of the updated solution. So we quickly go to the solution. Taylor expansion. I don't understand the last step of the updated solution. This one with the T, right? Yeah, I mean, there are other ways to solve it. Yeah, basically, what you can do is you can use the fact that we pick T such that f of x tilde is equal to 0, right? This is how we choose a root point. What root point means. Function evaluates to 0 at that point. So basically here you replace x by x tilde, which means mu plus t times x minus mu, and then you see this mu cancels out, right? Because you have a mu here, and then minus mu, and then this becomes the norm of t times x minus mu. And there's a property of the norm that's called homogeneity. means you can take out a factor inside the norm to outside the norm. You just have to make sure you take the absolute value. Then you basically get t times this norm minus theta, and then we know that it's equal to 0 because it's a root point and when the function evaluates to 0. And then you solve for t. So you find something like t equals theta divided by x minus mu. And then you can also plug this in here and you get the same solution. This is a bit of a shortcut that we took here. Yeah, where we use the basically we use this conservation property. Conservation again means that sum over the phi is are equal to f of x. Same as in Shapley values. So I agree, maybe there was this suggestion, there's a second approach, setting f of x tilde to 0 and then solve for t, and then you get the same solution. Okay, I hope it's more clear now. If not, we can also take it step by step. Okay, seems to be fine. Will there be point deductions in the programming part if we use unnecessary loops? Yes, typically yes. So yes, basically, if you do something unnecessary, we might deduce points. So typical examples are like a matrix vector product, for example. This can be solved as a loop, over each row of your matrix. But it will be very inefficient compared to native matrix vector multiplication in NumPy. I mean, it's a bit of a technical detail, but most of the linear algebra computations in NumPy are not actually executed in Python, but I guess actually in Fortran, which is there are very old implementations for linear algebra. So the thing called BLAS, I think. It's called Basic Linear Algebra Subprograms. You might look it up. So most modern libraries under the hood, they just call these functions that are actually from 1979, but they're very efficient implementations of linear algebra, and that's why it's much faster to compute a matrix vector product in one line in Python instead of a loop. And very often, machine learning, it's very important to have an efficient implementation. Otherwise, things become too slow. So in such cases, so usually we write something like make sure that your code runs efficiently, something like this. So if you read this in the programming exercise, it typically means there's a for loop that you should try to avoid, or there's like let's say a naive implementation that is very slow and involves a loop, and you can do it in native linear algebra like matrix or matrix vector products, and it will be much faster. The same is true for kernels. Typically, if you compute your kernel matrix in a nested loop, then it's incredibly slow compared to to an implementation without loops. So here's something I found. Just a quick Google search. Here's someone compared yeah, basically Python or let's say NumPy implementation against for loops. And you see sometimes you have an effect like a quadratic complexity, right? Which means your runtime increases quadratically with the size of the inputs, and probably also quadratic in the array operation case. But there's a multiplicative constant in front of your runtime. It is very, very small for these NumPy operations. So the runtime here you see for, I'm not exactly sure what this operation here is, but you see for relatively small array sizes can take many seconds in NumPy and just 0 seconds. Sorry, can take 40 seconds in a loop and basically below 1 second without a loop. So this is the kind of stuff where you should avoid loops. You post the link, yes, of course. Could you answer and explain this question from a previous exam? What is likely an overfitted estimator? A high bias model, a high variance model, low bias model, low variance model. Yeah, right. So overfitting is typically associated with high variance models. I think this topic was touched in the lecture about model selection. Lecture 7. Let's see. Uh, Here it is. The slide about bias and variance. So overfitting is what you get when you have a low training error, which is this dotted line. It's not written on the. Sorry. It's supposed to be the bias. I mean, overfitting essentially means you have a very complex model that is able to learn the noise in your data. And this corresponds to a model with high variance, as you can see here. So we go back a bit. There are these more like comic figures here. Yeah, maybe if you look at this one, you see there's this function that has a high variance. It fits every data point perfectly, but this typically means that you're learning the noise in the data. So this is typically associated to high variance. Mm. Yes, I think this is the one is the relevant plot. It's a bit okay. I see. It doesn't really say overfitting, no? But it's basically this model complexity thing that's associated to overfitting. Learning the training data by heart, and then having a large error on unseen data. Only one answer is correct in all multiple choice questions. Yes.
But one question to that, wouldn't the
Yeah.
low bias be correct as well when we go to the right when we talk about model overfitting? So when we have a complex model, we have a high variance and a low bias. So could you argue that overfitting happens when we have a low bias as well? So then C would be correct as well. Or?
I mean, your error is like a sum of bias plus variance, right? So if your error is large, and it's either because the bias is large or because the variance is large. And either of these terms being small doesn't really tell you about your error. So the larger of these two terms dominates the error, right? So low bias is not necessarily a sign of overfitting. In this plot, I think it shows something in one dimension, but it's actually two-dimensional, right? Because you would need one dimension for the variance and one dimension for the bias. A bit so simplified, I guess. So no, low bias is, I mean, low bias means that basically that your estimator approaches the true value if you have enough data. And overfitting means something prevents you from learning the correct parameter. So ideally, we want low bias and low variance, because this will be the best estimator. Can you explain exercise 3C on the second exam? Okay, so I think you're referring to this Freitagsrunde. We can check. Second exam 1920. Exercise 3C. Yeah, I would not use this geometric series. So let me share this. As I said, these are not our solutions. So there's a question about maximum likelihood and Bayes, where you have a distribution, and then you should evaluate probability that a measurement is strictly larger than 1. And the people who wrote the solution, they argue with a geometric series, but I think this is too complicated. So but I think this is the right approach. So the basically K is a natural number, at least 1. And so the probability that something is larger than 1 is just 1 minus the probability that it's equal to 1. And this term is easy to compute. It's just this one here, right? Basically, theta, 1 minus theta. 1 minus theta. So yeah, I mean, if you do it by a geometric series, then you still get the points, but I think it takes much longer to do it this way than this way. Yes. Yeah. Yeah, apparently this term equals 1/3, but too complicated. Yeah. So it's not how I would learn it. So I would use this 1 minus trick, but for completeness, this Wikipedia, there's this thing called geometric series, which is a sum over exponents going from 0 to infinity. Right? And you have some vector A and some basis R. And then there's a formula to compute it, which is A divided by 1 minus R. And this is probably what they did in the exam, but as I said, it's not how I would do it. Yeah, right. So maybe one thing might be useful to you is this, download this book by Duda and Hart, and classification, especially for the first 4 lectures. They're really based on the book and maybe provide a bit more context. I can send you a link. You can also find it on Google, or I guess there are other resources like Anna's archive, maybe. Yes, it's also on this archive. So these a very valuable resource in this book. Especially when it comes to the first lectures. You can also find it in the library. If you prefer a paper version. All right. Yeah, so feel free to ask more questions. No? So we have 15 more minutes. We'll just turn off my camera for now, but you can still read the chat and turn it back on once we have a question. All right, the next Q&A session begins at 4:15. Will be given by Hannah Ingwald. So Adrian asks, do you have any recommendations for the exam that were not mentioned before? Not really. So can we suggest you to repeat the homework exercises, right? So the theory questions and the programming questions. Read the lecture slides and maybe the book, and You can also use these exams on Freitagsrunde. And I mean, I would not learn too much with those because sometimes there are things missing in the question or there are mistakes in the solution. So yeah, I mean, it definitely helps to get an impression about the time, how much time you have, and how much you have to do that time. But the exact questions and solutions are sometimes faulty. Freitagsrunde. Um, there's one thing I could recommend, probably not for the exam, but just for you to learn more. There's a relatively old channel on YouTube called Mathematical Monk, and he has a very good series on machine learning, which is I think 160 videos about, and there's a lot of overlap between in the series and machine learning one. Yoda asks, will the difficulty of the exam task be similar to the wrap-up session and the length of the answers? Hardly. Hardly, I would say. So let me quickly look at this wrap-up session again. I would say generally the questions might be a bit longer. Maybe would expect like one more question on average than in the recap session. Yeah, a little bit longer, like yeah. And there's another question. Do we need to apply the activation function on the last neuron in a neural network? It has get some exercises, have two classes, 1 and 0. And we do y equals a4 equals sigma of a sum you see that one of the neurons is activated and the sum is larger or equal to 0. Hmm. Yeah, so typically not. Typically the output, like the last layer, is either a linear layer without an activation. And there are only a few exceptions, I would say. So one exception is some people apply an age or sigmoid in the output to restrict the outputs to be between 0 and 1 or -1 and 1. This is typically if you have a model that outputs data, like a model that generates an image. You very often have a function that pushes the outputs into a predefined pixel range. In other cases, not. I mean, for training, we often use softmax, right? But this is more like, I would say, it's more like part of the loss function. No, the loss is typically like a divergence between the training data and the output of your model, and then yeah, people apply the softmax, but softmax is similar to what we saw in the context of discriminant functions, right? So basically applying the softmax doesn't change the argmax, its arguments. Yeah. So just to make a decision, you don't need a softmax or anything else. I mean, as I said, there are exceptions, but generally for classification, you don't need it. There's a follow-up question. Whether we need the output to be 1 or 0, would have to apply sigmoid, because one of the sum is equal to 2. Those two neurons are activated. The y is equal to 2 without the activation. Yeah, that's what I said. That there's some problems where the output needs to be in a certain domain, like between 0 and 1, and then it will apply a sigmoid. It's like a, I mean, yeah, like the sigmoid is puts it between 0 and 1, and h puts it between -1 and 1. I guess there's one setting in classification where people apply the sigmoid, which is in multi-label problems, which is not covered really in machine learning 1. So you can have problems where a data point belongs to more than one class. You can think of images that have multiple objects in them, like a cat and a dog, right? So maybe you have images that only have a cat, you have images that only show a dog, but there are some images that have both, and they also have both labels. This is a typical case where you would use a sigmoid. No? But practically it's like I mean, okay, I don't want to confuse you too much, no? So I think it's for the exam, it's relevant to know that typically your output is just a linear layer. No? I mean the ReLU activation. No, even the ReLU, you wouldn't apply the ReLU at the output. So I mean, yeah, the typical problems in machine learning 1, the classification problems are just binary classification, which can actually be solved with a single output neuron, right? And then you just take the sign of the output, similar to an SVM or boosted classifier or LDA. All these classifiers, they just use the sign of the output to determine the class. And only if you have multi-class problems, then you would need more than one output. All right, so I think we're done for now. So there are three more Q&A sessions for you to attend. So yeah, if you still feel like you have questions, I just recommend you to visit these exercise sessions and sorry, these Q&A sessions. And yeah, so just have good preparation for the exam on Friday or all the way in 3 weeks. So thank you all for coming, and see you probably on Friday. Bye-bye.